Hi, welcome to the webinar. We will start in approximately 3 minutes from now. We'll wait for more people to join in. Thank you very much for your patience. Hi, welcome to the webinar. Thank you very much for your patience. We will start our proceedings. Today's webinar is about the entire mold making process on how it is done inside SolidWorks and SolidCAM, including some very interesting tools that we have inside SolidWorks. Uh, and the most important thing is how these tools are integrated in the entire process and how they talk to each other. For example, if you have done the entire process, this is what we are going to see today. We have a part, we will do the core cavity and slider separation. We will then go on and do the electrode extraction and then do the cam for one particular insert. And then we will go into a real life process where we are going to change the main part itself. We're going to put some changes into the main part, and we will see how the entire integrated system takes care of propagating these changes seamlessly right from the separation of core cavity being updated, electrodes being updated, the CAM being updated, the drawings being updated, how this is done completely in one process. So this is what is the process that we are going to look at. So if I go ahead with my presentation, today the process flow is pretty much what you see on the screen. You have got a CAD part. Uh, it could be a SolidWorks CAD part. It could be an IGS. It could be a Parasolid. It could be a step. So you have that part file, and from the part file, you go and create the core and cavity separation. And sliders also, if they are there in the part, we also separate the sliders. From here, actually, three processes can be done simultaneously once the separation happens. One user could take these parts and start the mold design. And in simultaneously, another user could pick this core cavity parts and start making the electrode design. And the third process that could simultaneously go on, it will be the CAM generation using SolidCAM. So for each of these, we have got tools within SolidWorks to work with, and all of them are gold certified product. That means they have got very tight integration with SolidWorks, and they work seamlessly inside SolidWorks in a unified single environment. There is absolutely no environment change when you move from one area to the other area. The environment remains same, the tool remains same. So basically what you're seeing right from the start to the end is only SolidWorks screen. So for each of these process, we have a product. For example, for the main CAD, we have SolidWorks. For core and cavity separation, we have what we call a SplitWorks. For mold design, we have MoldWorks. For electrode extraction, documentation, and design, we have ElectrodeWorks. And finally, the most important part of this webinar, the CAM, is being handled by SolidCAM. So you can see that although they are 5 different products, they are integrated into one system and they are seamlessly talking to each other. It's in spite of having 5 different areas of working, they all talk to each other using a single unified database of SolidWorks. So if there is any change, everybody knows what the change is, where the change needs to be updated. Everything is known to the product. So let's start with the first one, which is basically SplitWorks. SplitWorks is a revolutionary product. It uses quite an advanced technology to automate the process of core cavity slider separation and creation for plastic molds, blow molds, aluminum dies, investment casting, wax molding, and ceramic technology industry. It includes advanced technology to update the inserts after any modifications or additions to the part, including if the part has been imported via IGS or Parasolid files. So let's look at that first step. I'm going to go back. I have SolidWorks opened here, and I'm going to open the part that we are going to start off with. Okay, so I have a part in front of me, and this particular part has been completely modeled inside SolidWorks. Okay, but what is not applied yet to it probably could be drafts and also the shrinkage. So what I'm going to do is I'm going to save this part as a copy, and we are going to work on the copy file. I'm not going to touch the master part. So I'll name it as split, and just close all this and open only the split part. The first thing that I'm going to do after opening this file is to apply the shrinkage. So I'm going to use a shrinkage of 1.5% to this applied uniformly all over. Okay, that's done. Let's save this. The next step for me is to go into SplitWorks and start splitting this part into core and cavity. Like I said, SplitWorks is pretty intelligent. The first thing that it expects me to define is the uh, plane of separation or the separation direction. Which direction is going to be my core cavity extraction direction? So for that, I'm going to use a plane here, this plane, the horizontal plane, and this is going to be my separation direction. So I'll go into SplitWorks and I'll click on split part. So you can see that it's using the split direction, and it has quickly separated the part for me. And you can see that there are 2 colors distinctly visible at the moment. One is a light green and the other one is a blue color. The legends are out here. The light green basically is the surface that belongs to the cavity side. The blue colored surface belongs to core side. Then there are some surfaces that are red in color. So these surfaces that are red in color, SplitWorks doesn't understand to which direction they are going to belong to, because it's not possible that they could belong either to core, they could belong to cavity, or probably they could be completely different like a slider. So this red colored surface, what it has said, it's saying is it could belong to either directions. Then you have got another shade of green which says these surfaces do not belong to either one. SplitWorks doesn't understand because it doesn't have any draft. And then it also knows some surfaces belong to cavity, probably don't have a draft, but it thinks that they belong to cavity, so it moves them to cavity. And some surface that do not have draft, for example here, the cyan colored surface, it belongs to core but doesn't have a draft. So it's actually telling the user that these surfaces don't have any draft. And then there are red colored surfaces. Okay, so I'm going to accept the first initial result as they are and say okay. So what it does basically here is it creates a tab, and within the tab it creates a cavity group, it creates a core group, it creates two more groups called side core 1 and side core 2 by default. Whether a part has it or not, these two groups are automatically created. Okay, although they are empty, they don't have anything. And then there is another group called extra faces, then there is a group called no draft core, there is both directions. So it creates these groups. Also, you can see here, let me change the background color to rooftop. You can see that there is a yellow colored curve that is going around. It's also identified the parting line. Obviously, we are not going to use this parting line. We're going to make changes to our design. We are not going to keep the same parting line. So I'm going to hide the both open and closed parting line, and let's visualize the part. Now you can see that in the cavity side, there are two surfaces that actually are belonging to the core and they are moved to the cavity side. Probably what I feel is if I do a draft angle analysis with the top as a reference plane, you can see that there are undercut. So they are having negative draft. That is the reason SplitWorks has moved the surfaces to the core side. But this is not right. Probably there's something wrong in the design. We need to fix this. It's simple to fix it. I'll go into the features and I'll add draft using this as a neutral plane. I will pick the surface for which I need to apply the draft. And I would like to apply a draft of 1 degree. The moment I say OK, SplitWorks will run the function again and it will move that surface, which now has positive draft. It will move it to the cavity. I'll repeat the same function also for this, with this as a neutral plane and that surface to which I need to apply draft. They're moved to the cavity side. Okay, so more or less, this looks okay, except for these two areas here, which I need to now make decision on how my side core is going to be. The easiest way to make a side core is to have the spin move to the slider, which means that I'm going to have a hole coming out from a core insert, which needs to be machined. Now, when you have a hole coming from the side, imagine it adds to the complexity of machining. It means that I need a 3+2 machine to accurately go and drill the part or drill the hole and then do some kind of a boring to make it pretty accurate. This is going to add to the cost of my machining. Not only cost, it will also add to my complexity of the whole design itself. Instead of that, I would like to make a small change, and that change will ensure that this particular part can just be done on a simple 3-axis machine with a little bit of EDM work, which probably will work out more cheaper than taking this onto a 5-axis machine. What I'm going to do is I would like to create a plane. Before that, let me save the file. Okay, I'm going to create a plane on this particular face, say coincident, and I'll create a split line between the plane and these two surfaces here. And the same thing I'll repeat on this side because they both are on the same side, same dimension. And I'll repeat the same split also on the other side by creating a plane. Coincident. Let me insert a split line again between this face, and also this face. Done. Once these split lines are ready, I can now assign my faces to the directions of sliders. It's pretty simple. I can either right click on the face and say move it to side core 1, But sometimes if you have more than 2 or 3 faces, it becomes a tedious work to keep selecting one each of them. Instead of that, I'll go into something called as smart selection, and I'll select the faces 1, 2, 3, and 4, and I'll say these need to move to the side core 1, and I'll move it. So it assigns a new color to the to that group. Now this is my side core 1, and while we are here, I'm going to pick these surfaces which did not have any draft and said that they were belonging to the core. I'll move them to the actual core itself. Okay, that's done. Same thing I will assign here. I'll pick 1, 2, 3, and 4, and I'll move them to side core 2. And while I'm here, I'll also pick these 2 or 3 surfaces here, and I'll move them to core. Done. So I have got side core 1, side core 2, cavity, and core. Perfect. Now, for sake of visualization, I'm going to assign opening directions for each of these cores, because SplitWorks still doesn't understand which side these cores are going to open. So I will assign an explode direction that way, and I'll also define an explode direction for the second one, normal to that. Done. So more or less my design is ready. And if I go again into SplitWorks, I can explode the part, and this is how my core and cavity look like, and the sliders, of course. Okay, so I can do a nice visualization of how my directions are going to move, and this is how my entire thing looks like. Okay, so my basic splitting of core, cavity, and slider, they're done. All I now need to do is to create what we call as a unified body for each of these elements that I just created, the 4 elements: core, cavity, side core 1, side core 2. So I'm going to right click on cavity and say create surface. So it creates a unified body for me. I'll explain to you why we need this unified body. Right click on core, create surface. It's automated. It's nothing that needs to be done manually. Side core 1, I'll say create a unified body. Side core 2, create a unified body. So I have got the bodies. Now, why do we need this unified surface? We need this unified surface so as to create our parting surfaces. Creation of parting surfaces becomes much more easier and a lot more automated when we have these unified bodies. So our next step now is to create the parting surface, both internal as well as external. So to do that, I'm going to start off with a cavity, and I have got these areas that need to be plugged. So the first thing I'm going to do is to plug what we call as the internal parting surfaces. So I'll plug holes. So what it basically will do now is to show me the unified cavity surface. So this is only the cavity surface that it is highlighting. And it's also showing me all the loops that it has selected so that I can close these loops. Now, in 99% of the cases, loops are automatically closed by SplitWorks. But sometimes you could have loops which are very complex and they run really in like a 3D curve. In that case, SplitWorks will not be able to do it. It will highlight the loop that it doesn't do. And those loops need to be created manually using the SolidWorks tools. That's the best part, that you can have a mix of SplitWorks functions and SolidWorks functions to create the entire part. In this case, the loops are very simple, so I'll just click on plug holes. So you can see that it is just plugs all the holes that are needed. If I go below, you can see even this area, it's been plugged. This area is plugged, and also the top one. Okay, perfect. Once this has been done, we can now start with creating the external parting surface. Okay, it's a very important aspect in the entire process, is to create the right parting surface so that manufacturing becomes much more easier. Okay, when you're creating a parting surface, always we have to keep in mind the machining process. Creating too many sharp corners will either create the need of making more electrodes or using tools like flatten mill to get closer to the sharp corner. So we try and avoid as much as possible sharp corner situations in parting surfaces. But sometimes they're not avoidable. Sometimes they need to be created. Okay, so we are going to use a very powerful function within SplitWorks to create the parting surface. And that powerful function is called as loft. Now, loft itself has got a lot of internal functions that it uses to create the parting surface. But for a user, it's just one function. So I'll click on loft. So it's picked the unified body. Now it's just asking me to pick the start and end vertex of the parting surface. So for me, the start vertex is here and the end vertex is here. And it immediately creates the surface for me. I only need to provide the width of that surface, 75 millimeter, and I accept it. The advantage of using loft is that it runs two functions. One is creating of the parting surface, and the second is stitching of that parting surface to the unified body. So this thing is done automatically by SplitWorks. Let's run the same loft from here to this one. And here it's going to be 75 millimeter again. Okay, that's done. Okay, we have our parting surface. Now the front parting surface. Now this can be, if I'm a lazy designer, I could perhaps use the automatic tools and just do it. For example, I can still go into the loft. I can say this is my start, this is my end, and it will create the loft. But this is going to create problems. This is a sharp corner here. It's going to create problems for me in manufacturing. And even if I am successful in creating the sharp corner, when the two inserts are matched, when they do blue matching of the inserts, that's where you could have mismatch areas. So we will try and avoid this situation. So I'm not going to use the automatic function of loft in SplitWorks, but I'm going to use the sweep function in SolidWorks, where I'll pick the two edges, and that's how the surface comes up. Looks okay. But the problem is when you're using sweep, it'll always go normal to the curve. So you will come up to a situation where you'll have this gap. But we are going to accept this gap. And I'll add another surface using loft function. Here, let me remove this. Okay, and the start constraint is tangent and the end constraint is also tangent. Okay, perfect. We have done that, closed it. Like I said, when you're using the loft function of SplitWorks, it also runs this stitching. But when you use SolidWorks function, the stitching has to be done manually. The knitting has to be done manually. So we are going to insert, or we are going to add a knitting function. I'll pick the body with the surface, and I'll pick these two surfaces that I just created using SolidWorks, and I'll knit them. Okay, that's done. Let's move further. Let's go into this area where I need to create my parting surface. Here I'm going to use loft again. So I'll pick the start vertex and the end vertex. Now here you can see that the surface is going normal to the curves, that one of the curves it picked and it's going normal. That's taking an angle of 139. And I don't want it like that. I want it to follow this reference edge. And I'm not going to give a distance, but I'm going to give up to this vertex. Okay, say okay. SplitWorks comes up with a message saying that it's activating what it's called as a SplitWorks redundancy. SplitWorks redundancy basically says that, or analyzes the part and checks if it can, or if it's able to do the entire surface. If it feels that certain area or certain patch of the surface it's unable to do, it pops up this message and tells the user to check the result after it is done to see if there are any missing areas. Okay, in this case, you can see that SplitWorks Loft was unable to create this area for reasons that's best known to it. But we are not going to stop here and analyze why it went wrong, but we are going to move ahead. Again, I'm going to use SolidWorks functionality. I'll make a 3D sketch, a spline between these 2 points, and I'm going to give a tangent constraint to either side of this curve. Okay, this is done. I'll convert the edges that I have. and get out of the sketching mode. And in the surface, I'm going to use a function called fill. Okay, that's filled up. Accept this. And since it's created by SolidWorks, we need to run the knit function again. So these two areas to be knitted, done. Perfect. What remains is in the front. Now this is going to be pretty simple. So I'll go to SplitWorks, loft again, select two vertex, just define the width of the surface I need and accept it. That's done. So I have finished my parting surfaces. Now just to check if there are no gaps in between, I'll just right click on the outer edge and say select open loop. So it's just showing me the loop outside, which basically is telling me that I don't have any open areas inside, which is a good sign. Okay, so I'm more or less done with my parting surfaces. We go to the next step, and the next step is creation of the solid inserts. So we have got the next step of creating solid inserts here. When I click on the Create SolidWorks icon, SplitWorks will immediately create an assembly document. And in the assembly document, it has got the main body, which is the core cavity along with the, or even core along with the parting surfaces. So it's asking me to select the surface body on which I need to create the inserts. So this is the surface body. It has its own intelligence by which it determines the best possible fit of a insert. So it's created an insert. Now there are various ways of creating an insert. Currently we're using what we call as a symmetrical box blank. Means it'll have equal distances from the origin. You could also have a non-symmetrical box blank. You could have a cylindrical box blank, or you could even have a user-defined box blank. For example, there are several companies that buy material from a supplier. Let's say Bowler. They buy supplier, or they buy the blanks from Bowler, and Bowler has got some standard sizes. So what the user does, it's a one-time job. He creates a folder and he creates all those sizes as a just a simple model with all those chamfer and radius, and keeps it ready for him to be used whenever he creates the insert. So you can also have, or you could also define a user-defined blank. Now, if you look, what is the size that it has taken? It's taken 255 by 180. I want to change this. I would like to go 250 by 175. Chamfer. The chamfer here is 1 millimeter. I would like to change that. I would like to go with 2 millimeter. And the corner radius is currently set to 10. I would like to make it 20. Why? Because when I create a pocket inside my mold, in the mold plate or in the cavity plate or core plate, I can easily mill it with a pretty large tool. It'll make my milling life much more easier. Okay. And as far as thickness of these blocks go, you can see that the core cavity insert has got 65. I'll change it to 70. And the core insert has got 65 also. We'll change it to 70. And once I'm done with the size, position, and thickness, I can accept this result, and I'll click OK. SplitWorks will immediately create two inserts inside the assembly, the core insert and the cavity insert. Okay, so if I open the assembly, you can see that there are two inserts that it has created. The main part, which I'll hide because I don't want to see this now. There is a cavity insert, and then there is a core insert. So let me switch off the transparency. So I've got both of them. I'll switch off the core for a moment to show you how the cavity looks like. The cavity looks just like that. It's not yet complete because it has got the pins. We'll come to it in a bit. Let's switch off the cavity. I'll show the core. The core also is done, except for the fact that the sliders are still fused into the core. So we are going to start with the sliders. We're going to extract the sliders out from this core insert. So I'll save this. I'll go back again to my main part, and let's focus on slider 1, yellow colored area. So I'll right click on side core 1 and I'll say plug hole. So it isolates the slider 1 for me to make the design. Okay, that's done. And it's identified the loop that needs to be closed. So I'll close it. And then I can simply click on create side core, select the surface and the direction, and define the length of my side core part and accept it. That's done. I'm going to save this file and let me open the assembly. It's updating and you can see that the slider is now taken out from the core insert part. Okay, that's the first slider. Let's focus ourselves on the second slider. Save this. Okay, let's go back to the split. Let's go to side core 2 and I'll say plug holes. Okay. So that's the slider number 2. I'll fix the loop and I'll create a side core using this face and this one as the direction. 75 millimeter. Accept it. Okay, so the slider is created. Go to save this and let me open the assembly again. Okay, the sliders have been removed. They still belong to the main part. I'll switch on both of them. And since the sliders are more than the insert, I would like to just trim them off. So I'll edit this part and I'll create a plane on this face, coincident. And we will use the cut function with surface. This particular one, other side. Perfect. Let's repeat it on the other side before we go to extract the inserts. Select, coincident, done. Cut with surface. Not auto select. I'd like to select this one, change the direction. Perfect. They are done. So as you can see, they still belong to the main part. They're not still belonging to the assembly. So we need to add these two, remove from the main part and put them into the assembly because we need everything to be a part of the assembly. So I'm going to go to SplitWorks and I'll say add side cores and I'll pick side core 1, side core 2, and I'll give them their proper names. So in the tree, they should appear as side core 1, this one, and the second one should appear as side core 2. Let me save it. Okay. Once I've done OK, clicked OK, what it is going to do is basically it's going to take these two items out of the main part and put it into the assembly tree. They no longer belong to the main part. They will now belong to the mold assembly itself. So you can see that in my assembly, I have got two paths, side core 1, side core 2. Just run the rebuild. Okay, we'll come to them a bit later. Let's hide this and let's switch on the core insert because we'll work on the core insert. Now, since these are protrusions, we need to have pins here. We can't have them as part of an integral core. It's going to damage it's going to be damaged while we are doing the machining. It's not easy, or no, it's not practical to have these protrusions in the cavity and then do machining. So we need to add them as core pins. So these are going to be subinserts. So I'm going to edit this part and let's create the sketch for my subinsert. Okay, to the white, simple, round, just make a circle, diameter 5, diameter 10, radius 5, sorry. And also here, This is done. Okay, let's get out of the sketch. And we go into SplitWorks and we have an option called as Add or Create Subinserts. So I'll click on Create Subinserts. It identifies the sketch and it's already ready with the subinserts. What we have to do only is we need to add the base to it, not straight, but I would like to have a base with depth of 5 millimeters and diameter of 15. So let me create that. And sub again, circular 5 and 15. Okay, this is done. We extract the pins. You can see how it's working. One of the ways it's working is it is not expecting the user to do all the dog work of running the commands. The user only has to know what to do. How to do is being done by the software itself. Okay, I just created a sketch and said, this is my design. Now you create the pins by yourself. So it's running all those commands which otherwise would have been manually done by the user in the background, creating that, putting them back into the assembly. Somebody asked me what is the advantage of having all these products versus different softwares. The biggest advantage here over the likes of, let's say, Cimatron, TopSolid, or even the likes of NX or PTC is the fact that the software is very easy to use. It has got the element of SolidWorks running all the way right from start to end, and it has got the best of all products. It's not that we are very powerful in design. We also have design. We also have very powerful electrode design. We have got a very powerful CAM. All have come together to give you a very powerful product for mold making. Let's hide this sketch, and you can see that there are 3 core pins that it has extracted, and each of them have been given a name, sub 1, sub 2, sub 3. You can change these names later on. Let's hide the pin, and this is how the mold looks like. Okay, we'll come to core insert, cavity insert when we are doing the CAM. So I'm going to save this. Yeah, save all. I'm going to open the core insert now because I would like to run a similar function that I did using a core insert. So I'll make the sketch again here. Okay. And I would like to make the pins, sorry, for the bottom. Okay, let's go to the top view. Okay, so the pin also for this area here, and this pin here. And here we are actually going to have not 3, but 4 inserts. I also would like to extract the insert for this region. So I'm just going to make a rectangular sketch here. Dimensions I'm not interested at the moment. I'll exit and go to SplitWorks and create subinserts. So again, it knows the sketch, it knows the part. Okay, somebody asked if there's a change, what happens? I think it's Goran. I'll come to it. It's a very interesting thing, but I'm going to come to it. Not a small change, but it's going to be a major change we are going to introduce. Okay, so let's go ahead, provide the circular base here. Let's go to the circular base. 15. This one also is a circular base. 5, 15. And the last one, however, is not a circular one, but it's a rectangular one. 10 millimeter is the depth, 35, let's say, is the width, and 50 millimeters is on this dimensions. Okay. Once this is done, just say accept, and it now starts extracting the inserts. Not only extracting the inserts, but it's also going to place them out in the assembly tree for me. Takes few more seconds before it puts them back into the assembly. Okay, it's extracted it. Now it's going to place each of these pins and the square insert into the assembly. Okay, that's done. So you can see sub 4, sub 5, sub 6, sub 7. So it has made the inserts for me. You can see that they are already here with a different color. I'm going to switch these off so we can see the cutouts here. Let's switch off the sketch also. So I have the cutout, the back, I've got their heads. Okay, so more or less we are done. So I'm going to save all of them. Okay, we'll move to the next step now. Oops, sorry, should not have exited. Let's start it. Okay, so I'm going to go to the next step, which is basically extraction of the electrode. So we are going to move in the next step, which is the electrode extraction. And this particular area is handled by the product called ElectrodeWorks. ElectrodeWorks automates all aspects. Sorry about that. ElectrodeWorks automates all the aspects of extraction, design, management, and documentation and manufacturing of the EDM electrodes. It's fully integrated into SolidWorks. It's a gold certified product, and it guides you through the entire design and production process. The best part here, because it's completely integrated, it will still understand if there are changes coming in from the main part. Okay, so let's go open our core insert. So I'm going to open the core insert here, and let's extract a couple of electrodes on that. So I'm going to hide this. Okay, and let's go to ElectrodeWorks and say add electrode. Okay, so what it does basically is the moment I click on add electrode, it creates again an assembly file. It's asking me for the name, so I'm going to say it's core electrodes. This is the name of the file, and it brings in the core insert into the file, and it waits for the user to start extracting the electrodes. Okay, so I have the core insert here with me, and it's opened up the blank window for me where I need to select what kind of blanks I'm going to use for electrodes. Now we have got several blanks. For example, we have got the 3R blanks, both inch and millimeter. Then we have the regular blanks, Arova, and then you have got user-defined blanks where the user who has got a supplier with a certain amount, it's either copper or graphite. So these are the only two materials that are used for EDM. So they can have standard blanks with them, and that can be kept into a folder and they can be called anytime. I'm going to use the 3R which also has the holder to it, and the two-step blank. Okay, so there are several ways of extracting the electrode. Now, the area that I'm more interested in extracting is this region here, because this is just not possible to do milling of. So this needs to be spark eroded. Okay, so for that we need an electrode. There are several ways in which electrodes can be extracted, and the fastest way is to have a seed face or a reference face. Once you identify a reference face, ElectrodeWorks will find the connected faces of that reference face and create the electrode for you. It's very, very simple, okay? And it works when you have ribs and other things where the geometry is very well defined. So I'm going to use a seed face, and I'm going to pick this reference face here. You can see immediately it identified all the relevant faces of that electrode, and it made the electrode for me. Sorry. Okay, so it's showing me an electrode. I may accept it, I may not accept it, I may change it. I'm going to change some things in this electrode. First of all, you can see in the position, there is electrode coordinate system. So there are 4 possibilities of an electrode coordinate system. Currently, it's at the base of the electrode where the holder sits. There's another possibility where it is at the base of the electrode, the burn profile. The third possibility is it's in between the burn area and the base of the electrode, somewhere in between on that step. And the fourth possibility is it will find the minimum reference point of the electrode and it will put the coordinate system out there. I do not want that. I'm going to use the second one where I'm going to put the coordinate system on this particular face here, this one, this face. Okay, so that's where I want my coordinate system. Also, I would like to make some changes to the width length because this is too big. I'm unnecessarily going to waste a lot of copper, which is pretty expensive anyway. The size is going to be 85 by 18. Okay, and the thickness, obviously, I just want 20 millimeters. I don't want to increase this thickness here, so from the total length, I will remove about 20 millimeters. That's my electrode. Once this is acceptable to me, I will simply go here and say, add this electrode. Okay, the electrode is extracted. So if I run the animation, this is how it's going to look like. Can pull it up, go down, and this is how my electrode is. So if I switch off the electrode for a moment, I hide the electrode. You can see ElectrodeWorks also colors the surfaces that were used or were defined as the burn area in the electrode. Why are these necessary? When this particular part is sent down to the CAM environment, when it goes into SolidCAM, the user who is using it realizes that this area is going to be burnt. So he doesn't waste much time in trying to mill it completely. So he knows that these are reference areas. These are anyway going to have an electrode. So I'm not going to waste much time. I'm going to focus on other areas. So these areas are marked automatically by ElectrodeWorks. So I'll again show the electrode. The next thing I'm going to do here, which is a very critical thing, is to add the spark gap to it, uh, which is very complex process, but we have simplified here. I'm going to add a spark gap to it, and I'm going to use 0.1 millimeter as a spark gap for my electrode, and I'll accept it. You can see that it's already added the spark gap here. Okay, it's already added to the electrode. Another thing, what we can do inside the electrode is to extend the areas, because you can see that this area is exactly stopping here. I don't want it. I just want to pull it out a little bit more. So I have an option to add clearance in this direction with these 3 surfaces. And I'm going to use tangent, sorry, not normal, but tangent, 1 millimeter, and extend it. Okay, so it's pulled out. You can do the same thing also on this side, add clearance to this direction. And these are the 3 surfaces that need to be added onto the clearance. Tangent 1 millimeter. Okay, this is done. This electrode is done. I'm going to hide this electrode. Let's focus on another area which will need an electrode, and that's this sharp corner. Okay, again, this is not very well defined. So I'm going to need an electrode there, because no matter what process I use in milling in 3-axis, I will have the cutter radius left out, probably R3, R4, depending on the last tool I use. So I will add another electrode, and this time the method in which I'm going to add the electrode is not going to be by using seed face, because there's no reference face here. Everything is pretty huge. So I will use the faces function, and I'll select the faces manually and say that this is the area that needs an electrode. Once I've selected it, I'll calculate an electrode. So that's the size that it has calculated. I'm not happy with the size, so I'm going to change the size. This is going to be 20 millimeters, and this will be 40. Okay, only thing I need to change now is the position. Again, coordinate system number 2, and in the position I'll just type in a value 48. You can move it up and down. Okay, but 48 looks pretty much okay here. I still have got a lot of gap, so I'll accept this electrode. Somebody is asking me a question if we can use 4 different modules and 4 different PCs. Yes, as long as you have 4 licenses of SolidWorks, you can use them on 4 different PCs. Okay, this also is done. The electrode, if I switch off this, you can see that my electrode is extracted. But I have a problem with this electrode. The problem here again is I've got another sharp corner. Now this corner is the exact corner of my core insert. So if I make the electrode as it is, first of all, it's going to be very difficult because it's a 3D corner. Assuming that I make it, when I'm doing the EDM, there's every chance that the corner might also get eroded and I'll get a radius instead of a sharp corner. So I need to clear this region. So I'll add an electrode clearance to this with this as my direction, and I'll select these faces for which I need to add clearance. It's tangent 2 millimeters, but on the other side, that's it. I'll accept this. Okay, so this is how the clearances come. So if I now switch on the core insert, you can see that the electrode clears the corner edges. There is no more issue with the corner edges, and it only will do the erosion of the area that I want it to be spark eroded. Okay, so we have the electrodes ready already, 2 electrodes. My next process, and the most important process in this, is the documentation. Documentation is a breeze. It's completely automated. You can right click on the main electrode file and you say generate multi-drawings. So it's asking me to pick the reference part, which is this. It knows exactly there are 2 electrodes on this. You can, if you want, remove some electrodes from the drawing, but generally everything is included. So there are 2 drawings that are possible. One is the manufacturing drawing and the other one is the drawing for EDM. So I would like to have both of them, and the sheet size I'm going to use here is an A3 sheet. Okay, and accept it. Goran, you asked me about how you can define the clearance between the electrode and the model. I just showed you on one of the electrodes, I applied a spark gap. So that created the clearance. In event the electrode is really very complex, the spark gap may not work. In that case, the spark gap needs to be given as a negative offset when you're doing CAM. We can see that the drawings are automatically being generated. Okay. Done. So I can go into my window and let's look at the electrode 1, the EDM sheet of the electrode 1. You can see that the dimensions for sparking are given here, including the depth. Let's move the other side. Okay. And we have it here. The same thing if I take the other one, the second EDM. Okay, I don't want to, if you want, you can even switch off the column here and move it to the other side, 17.54. Okay, so I'm going to save everything, please. Okay, so let me close all of these files. My electrode is also done, so that process is also done. I'm going to close this. Close the drawings of both the electrodes and the electrode itself. Let's close it. Close. Okay, so my electrode also is done. What I have not done here actually is the actual mold design. Trust me, it takes some time. So I have already a mold built up. Towards the end, I'm going to show you the complete mold and how we create automatic drawings of the entire mold without breaking a single sweat. Okay, I'm going to show that also. Otherwise, it would have changed or increased the process completely. So my next process here is the CAM itself. So for CAM, we have got a very powerful CAM system that we can use to machine all the parts that you just saw: core insert, cavity insert, so on. So we have got generic high-speed roughing, we have got new generation high-speed roughing, we have got a revolutionary product called iMachining, and on top of that, we also have generic and new generation high-speed finishing techniques inside SolidCAM. So we're going to use a mix of these technologies to machine one of the parts, and then we are going to fire the change into the main part. Okay, so let's go here and open my cavity, because I'm going to machine my cavity now. Okay, let's switch off this plane. Now, before I take the cavity into machining, I would like to close those areas because I don't want the tool to get into this area. This is going to be anyway done by boring. So I will go to planar surfaces and I'll close the surfaces. All the three surfaces, I'll close it. Okay, and save it. And let's start SolidCAM. Today I'm going to use the version that we are releasing, the 2021 version. So the entire part is going to be done using this version. External. And to start off with, I'm going to use a Siemens machine, a machine with Siemens controller, 3-axis. And the next step is to create the coordinate system. So I'll just pick a planar face, and the coordinate system is coming in the corner. And plus it gives me several options where I can move it. So I'm going to pick the origin and move it to the center here. I can directly move it to the center, or I can move it even manually. Accept this coordinate system. Okay. My next is to define the stock. I have already machined the corners, so I don't want to waste my time on defining machining for corners. So I have already machined, and I've already got a stock with a shape, and that shape is defined by this boundary. Okay, accept. So that's how my stock looks like. I'll accept this. And the target is obviously this, but it has missed the surfaces that I created later on. So I'm going to pick the surfaces also as a part of the target. So SolidCAM works with both solids and surfaces. It works in the hybrid mode. So it need not be always a solid. You can have a combination of solid and surfaces. Let me accept it. Okay. We are into our CAM environment. Okay. And for reasons best known to me, I do not want to spend time defining the process again. I already have machined another part of similar size, and the process more or less looks okay for applying to this particular part. So what I've done is I've already saved a template of that particular mold into my template directory, and I'm going to use the template directly on this new part. The size is similar, but the geometry is not. The geometry is completely different. So I'll go into my templates and pick the templates, and I have got the template here called demo mold, and I've got the entire process here. Okay, so we have got roughing, rest roughing, horizontal finishing, linear finishing, geodesic 3-axis machining, which is a new, completely new toolpath type inside 2021 in SolidCAM. Again, we have a rest roughing, constant Z machining, linear machining, rest machining, and towards the end, I'll also show you again a geodesic machining for finishing the entire part. Okay, so I'm going to drag this template and drop it into my CAM manager. Say okay. So I have got my entire process here. Let me edit this process. It's a turbo HSR. I'll just select my target, 0.7 millimeters offset. The tool that I'm using is a 25R3 high feed bullnose tool. I'll save this. Go to the next process, which is a rest roughing. Okay, It's basically a roughing itself, but it's going to do rest roughing, and this is using a 12 with a corner radius 2 millimeters. And here I'm going to again use a target and the same 0.7 millimeter offset. However, we are respecting the stock, and I'm asking it to machine into areas where material remaining is more than 0.7 millimeters, so that it doesn't do any work in areas where material is like scallops are remaining. It doesn't go and touch that area. So I'll save this. My next toolpath is horizontal finishing. So I would like to finish all the horizontal areas before I again do a rest rough. In this case, I'm using a tool, which is this tool, new tool table. It's 12, corner radius 2, okay? And the constraint boundaries, I'll just pick the bottom curve here. That's the constraint boundary. Passes 4 millimeters offset, and we're using horizontal machining in the generic high-speed machining function. So I'm going to save that. So I have got 3 processes now ready to be calculated. I'm not going to waste my time looking at the calculation. I'm going to pick these 3 processes here, and I'm going to put them for parallel calculation, which means that calculation is going to run in the background. We can go ahead and start defining the next process. So I'm going to open the turbo linear machining. And here I have got, first of all, let me select the Z bottom. Okay. And here I've got 3 areas that I need to machine. The top parting surfaces I want to finish. I don't want the rest roughing tool to again run on that area. So I'm going to finish that by selecting the constraint boundary. Now you can see that my CPU is completely loaded because the new generation turbo roughing uses, it's a 64-bit system, so it uses the entire, it's already done some of the toolpath calculation as we are defining. So I'm going to pick the boundaries. Okay, that's the first boundary. No. Yep. The second boundary will be here. Oops, that's not the boundary. It's here. Oh, we have to wait. So I'll come out of this. My calculation is already done. So I'll go back again into the boundary creation. Okay, that's it. That's the first boundary. And the second boundary now. And this one, I'm not going to be using the parallel calculation. Okay, I'm going to use a completely different, sorry, that's not the, and that one. Okay, that's also done. Since the turbo machining is pretty fast in calculation, there's no point in putting it in parallel calculation. This calculation can be done right in front of us. You will be zapped by the calculation time of turbo. So here I'm using a 10 millimeter ball nose tool, and the passes I'm going to use 0.5, and the angle of machining is going to be optimally calculated by the software. It's not 90, it's not 45, it's not 0. The angle will be automatically calculated by turbo machining depending on the geometry. Okay, so I'm going to save this. Drive surface is not selected. Target, save. Okay, let's run the calculation. I don't need to do any parallel calculation. You can see the time it will take to calculate. 3 seconds, the calculation is done. Okay, so this is how I machine my top areas of my parting surface. That's done. The next one I would like to focus is on this region here, this area. I would like to machine it separately. So for that, we have got a new process. It's called as geodesic machining. Geodesic is nothing. It's basically a toolpath generator or toolpath pattern generator that uses constant step over, irrespective of the geometry that you're picking. So all I need to do is either I can pick on the model itself or the surfaces. So I'm going to pick the surfaces, and I'll say my curves will be determined automatically by the surface. The only thing I need to define is the constraint boundary. Yep, that's it. That's the constraint boundary. I want the toolpath to be within that. Tool we are going to use is an 8 diameter ball nose. Okay, let's save that. and let's calculate it. Even this calculation is very, very quick. Imagine that it needs to calculate a constant step or irrespective of the geometry that it's selecting or it's working on. How geodesic works here is it starts looking normal to the geometry. Rather than looking normal from the machining direction, it starts looking normal to the direction of the surface, normal to the surface itself. And this is how it generates a very, very smooth and a powerful toolpath. Okay, so that area is done. Now what I will do is I will simply put for calculation another rest rough before I run the finishing. So take the target. The tool here is which is this tool again here? It's an 8 diameter ball nose, okay. No reference tool, I'm going to use the previous stock here. Remember, there are a couple of finishing operations that have already gone in, so the stock has to be recalculated for rest roughing. You can see what changes have been done in 2021, especially in terms of calculation speeds. It's running the stock calculation of the previous operation. Remember, that's 250, 175 by 70. That's the size of this part. And all these calculations are happening actually live. Okay, 25 seconds. It's calculated. It's done. We can now safely assume that the part is now ready for running the finishing operation. We can put a semi-finishing if we need. Basically, semi-finishing is nothing but finishing itself with a smaller offset. Okay, so let's calculate our constant Z operation. And the constant Z operation is going to be done using a 10 diameter ball nose. And okay, constraint boundary. I want the constant Z to run only inside this area because everything else outside is already finished. So I accept this. Depth of cut is 0.3 and we have a slope angle between 45 to 90 degrees. So I'm going to save it. Yes. And run the calculation. We can again calculate in parallel, but don't need. The calculations are pretty quick. Okay, that's done. Z calculation is done. Let's change if I need to be the tool color or the toolpath color. Let's change it to blue so that it's more visible. So that's my toolpath for constant Z machining. We'll also now calculate for linear. Again, simple 10 diameter same tool. In the constraint boundary, again, I'm going to use the same boundary. We can name the boundary so that picking up the boundary becomes much more easier. Passes 0.2 and we'll save it and calculate it. Okay, it's done. But I have a problem here. First of all, there are a few retracts I need to fix. We'll come to it. But the main problem is it's running the toolpath on the edge, which is not good for me. Okay, but I've given this boundary, but still it's running on the edge. To fix that, we go into another very powerful function inside SolidCAM, and that's the toolpath editing. Okay, let's open this. And what I'm going to do here is I'm going to create a sketch. Line. Just create a line here. And one more line here. And what I'll do is I'll add a 3-point arc between this point. It's just that we are marking the area in which we'd like the toolpath to be edited. Okay, so that's done. Let's go into the shaded area again, and I'll right click on the toolpath and I'll say edit this toolpath with a boundary. Now this boundary is coming completely from a different direction. It's no longer coming in Z, it's coming in the Y direction. So I'm asking SolidCAM to trim off all the toolpath within this boundary and keep everything outside the boundary. And in the link, the best part in editing is I can change even the links of the original toolpath. So I would like to stay on the surface by 3 millimeters. Save, and let's calculate the edited toolpath. Oh, sorry. Let's calculate. Now the best part in editing, in majority of the softwares that do toolpath editing, the original toolpath is gone. You can't get it back. But in SolidCAM, the original toolpath remains as it is. It's suppressed. So if you make a mistake in editing, you could always go back to the original toolpath and re-edit it once again. Okay, so you can see we've chopped out the toolpath which was appearing on the edge, removed it, and what we have is only the toolpath inside. Of course, it's because of the resolution. Otherwise, this is how the toolpath looks like. Those retracts also have disappeared, so it looks a very powerful toolpath now. We'll also run the calculation of the rest machining. Okay, that's the boundary. I'll save it. Yeah. And I'll put this calculation in the background, put it for parallel calculation. And while the calculation is happening, I would like to select all of these toolpaths and run the simulation. Go into Solid Verify. That's my starting stock, and my simulation starts. So what I'm doing here is I'm running a couple of processes in the background. One, I'm running the toolpath calculation in the background, and the other one, I'm running the solid verification also. So I'm not wasting any time. The user is not wasting time. He's running several processes parallelly. So the most important thing here is actually going to be your system. And since many of our product of our toolpaths are utilizing all the cores, so if you have a system with, let's say, 12 cores or 24 cores or 24 processes, not cores, 8 cores or 12 cores. So if you have got 16 processes or logical processes or 24, the calculation time gets that fast. You can see the toolpath direction. It's automatically taken care by the turbo process. That's the rest roughing. And then the constant Z machining starts. Okay, let's stop it. Go out. It's still calculating. Okay, let's give it a few more seconds. Once this calculation is done, what we are going to do, okay, that calculation is also done. So I have got my rest machining also calculated. Perfect. So I have my toolpath ready here. I want to save this file. And what I can do also from here is I could take and generate a tool sheet. Okay, so I've got several formats. Since it's Excel based tool sheets, you can completely customize the tool sheet the way you want. I'll go with a couple of formats that I would like to show to you. Okay, so the first format is what appears on your screen. One of the formats where you have got the toolpath name, operation number, the strategy, tool number, cutter diameter, corner radius, the offsets, and the time basically for machining. Okay, this is one of the formats, and there are several other formats that we can look a bit later. Now I'm going to close this file because now we are going to do the most important thing. My process is completed and the customer is now walking in saying, I want a change in the main part. Now imagine if you're going to have 3 different softwares, one doing design, one doing core cavity and the mold design, the other one doing CAM, and you make the change in the software that's doing the design, the one that is doing core and cavity doesn't understand a thing of what has happened in the other software. And the one doing CAM will never know that there was a change that was introduced in the entire process, because they don't talk to each other. They could be standalone systems. The best part of an integrated system is that the entire process is seamlessly connected. So I'm going to open the main part. Let's go to the main part, which is the split. Okay, I'll open the main part here. And like I said, I'll change the I'll not make a small change, but I'm going to introduce a major change. The major change here is that I'm going to move the position of my slider itself. Okay, not some radius change or not some thickness change. I'm going to move the position of my slider. It's currently 40 millimeters from the origin. I'm going to change this and say 20. Okay, you can see SplitWorks automatically ran the updation. So SplitWorks is updated. I don't need to do anything. SplitWorks automatically updated everything. Okay, so I'm going to save this file. Once this change comes and I open the assembly of the inserts that I created, you can see it's again running the updation. And you'll see the side core move on the side. It's already done. We do have a small issue here with the core insert, which I will fix in a jiffy. I'll edit it. There seems to be some hanging surface out here, which is basically a body. I'm going to delete it. Okay, this is done. So I'll save this or save all. My inserts are also updated with the change. Okay, let's go out. I'm going to close the inserts. Let me open the electrode assembly. Okay, so core electrodes. Open the core electrode. Okay, it's given me an error. Why? Because we used a different method for this. We did not use a seed face method. If it was a seed face method, it would have moved automatically by itself. Because we picked this manually, it's unable to update this electrode. But don't worry, it's pretty simple. Okay, this electrode needs updation. I'm going to go into electrode. I'll edit this electrode. And all I need to do is to change the position, because the position, remember, was given by me manually. So I'm going to move this position 2 notches. That's it. And the electrode is updated. Okay. Once the electrode is updated, what should happen to the drawing? Let me save it. Save all. I will specifically open the electrode drawing or the EDM drawing of this electrode, because the change is here. So let me close this and open the electrode drawing. Let me go to the second one, electrode 2 EDM. Let me open this. You can see again there is an updation. From 17.54 it changed its value automatically here to 2.46. Okay, that's the new Y coordinate that it has taken up after the updation was done. So my drawing is also updated. I'll save this, close. Now comes the main part. The main part here is updation of the cam. So my user in SolidCAM opens this part, the cavity insert. Being a part of the seamless process, SolidCAM understands that there was a change fired into the entire process. It knows that there was a change that has come in. So immediately it pops up a message to the user saying that the design model was changed. Do you want to replace it? Options are yes, if you want to accept it. No, I don't think anybody would do that. Or ask me later. You're not yet frozen your process. You would like to freeze the process and then call in the change. That's when you say ask me later. So the next time you open it, it'll again ask you the same thing. So I would like to replace the model. Updated, the change is updated in my part. The cavity got updated here. I have my process. which is still yet waiting for the change to come in. And you can see it has put the rebuild icon next to the entire process. That means it's telling the user, you have changed your part geometry, please recalculate your toolpaths again, because these toolpaths are no longer valid for the part geometry that you have defined now. So I'm going to synchronize the target. That's done. And on operations here, I'll say synchronize all. Done. All I now need is to just select everything here and put it for calculation. So you could see that I fired a change in the main part and the entire process got updated by itself. Okay. Software that caters to your entire process and not bits and pieces that cater either to design, either to some portion of the design, or they cater to the manufacturing, no matter how powerful they are. The moment change comes, it's really frustrating to put the change physically in every of these softwares. It's almost like you're destroying the part that was already done, remove completely, start fresh again. As a user, it really becomes frustrating because if the changes are not one, they're going to be 5, 6 changes. You imagine every time there's a change, the user has to do a new part. So it's very important to drill this point home that we have an integrated system and the integration works seamlessly, whether it is part design, whether it is core cavity design, whether it is electrode design, whether it is mold design, whether it is CAM. The entire process is seamlessly managed in one single unified environment. While this is calculating, I hope I can open another window of SolidWorks. And I would like to show you some paths that have been done using the SplitWorks functionality. Okay, I can keep continuing the calculation. Now, because it's using a full CPU, SolidWorks is not finding much except this, sorry. Okay, I'm gonna close this. Let's open a pretty complex example that was done using SplitWorks. And this is a high pressure die casting die. This is also called as bell housing. I think it's a portion of the gear assembly in an automotive vehicle. Okay, let's go here and switch off all the sub inserts. I don't want to see them. And the part that was done was the center part. It basically has 2 cores. We can't call it a cavity, but they have cores basically, one coming from the top side and one from the bottom side. And you have got 4 sliders coming in 4 different directions to create this part. Like I told you, when we are doing the internal parting surfaces, if it's a fairly complex one, it'll still manage, but this particular parting surface was pretty complex for it. This area of parting surface only was done manually. Otherwise, everything else is almost automated completely. So parts like these also can be done using SplitWorks and then machined using SolidCAM. Of course, EDM also can be done on this. Let's not save it. We also have some relatively complex parts like this part here. Okay, this part is basically looks simple, but it's not. So it's a pretty complex part. It's got 2 sliders, 1 core, 1 cavity. This also was done using the SplitWorks functionality, electrodes, and then was machined using SolidCAM. So the entire process was done using the 4 items that I just showed you: SolidWorks, SplitWorks, ElectrodeWorks, MoldWorks, and SolidCAM. So the entire process is completely done using one single unified environment. So what you have here is a very nice updated toolpath. So all the changes of what were fired in the main part have been incorporated in my toolpath also. One nice thing that I would like to show you with 2021 is the fact that if I generate a G code now of the turbo HSR, let's look at the number of lines it generates. It's going to be a pretty lengthy toolpath. So if you look at the toolpath length, it's approximately 400,000 blocks. Okay. Now in 2021, we have got an option to do an arc fitting with arc fit factor equal to the tolerance of the cutting itself. So the tolerance is 0.1, so I'm going to use an arc fit factor of 1 here, and I'll just calculate this toolpath. So that particular G code was 400,000 points. Okay. And now if I generate the G code of this in 2021, okay, it's just 90,000 blocks. It's 1/4. We reduce it to 1/4 by introducing arcs into our toolpath. This facility is now available with the entire roughing functionality and also the finishing functionality of turbo. So we can fit arcs based on the tolerance that you use for machining. So it's a very powerful function in 2021. Of course, for 2021, we are going to have more webinars where we are going to explain to you what is new, but that's to a later day. Today, we have seen basically right from start to end how we can handle the entire process in SolidCAM. What I promised towards the end, I'm going to show to you is the mold. Yeah, here is the mold is here. Assembly. Okay, let's open this. Okay, so you have got MoldWorks here. In the plates, you have got the static and the mobile. Static is currently hidden. I'll just show the static, the other one also. So this is the cavity side, and then you have the core side. I'll show all. So you have got the complete mold done again inside the SolidWorks environment. And the best part with MoldWorks is that you can generate the entire drawings automatically of the entire mold automatically. So you can, whether it's plates, anything, just go to MoldWorks and say generate 2D drawings. It will ask you to pick a template. So there are several templates here: A0, A1, A2, A3, A4 portrait stuff. You can pick A1, and you can say, I would like to have drawings of this part, this plate, and this plate only. So there are 3 plates, and I'll say generate. So it will automatically generate all the related drawings. There are questions that are being asked, and somebody asked me if it's possible to watch this video. Yes, this is completely recorded, and by tomorrow, you will get the link of this particular. It will be there on YouTube, and you could watch this offline. Okay, this entire webinar can be watched offline. So that's it about the entire process. We started with a part, we did the core cavity separation, we did the electrode extraction, we generated the cam for the entire core cavity part. We went back, shifted the entire side core area itself completely in the main part. SplitWorks updated itself, ElectrodeWorks updated the electrodes, SolidCAM took the changes and updated the entire toolpaths. So the entire process done in one single unified environment, and that's why we call this to be an integrated CAD/CAM system. Okay, everything is available in one unified interface. Okay, these are the drawings. You can see that automatically these drawings have been generated, including the dimensions and stuff like that. Sorry. So I guess that's it. Anybody who is into mold making, who's into high pressure die casting, who is into investment casting can take advantage of this particular software with all the add-ons into it and do his entire process seamlessly without worrying about who is going to see the change, whether they're going to get the change or not, whether the change is going to be propagated down the line or not, so on. So don't worry once, and it's one directional, remember. So the main user, only the designer, has the ability to change the main part. So the moment the main part has changed, the uh, updation is propagated downline. Right. Thank you very much for watching the webinar. If there are any questions, I still have time, and we could ask the questions. We're exactly at 90 minutes, slightly less than that. So I believe it was a pretty useful webinar for all of you. And we are going to have another session of webinar probably next week, where we are going to focus totally on mold machining CAM part only, the SolidCAM part, where we are going to focus ourselves only on the CAM part. And there we are going to explore SolidCAM's powerful functionality for machining any kind of mold inserts. Somebody asked how SolidCAM would be useful in design of PET bottle molds. Pretty simple. PET bottle mold is nothing but a part that is revolved, and then you have got ribs of design. Basically, there are designs, and once you have that, you can still use SplitWorks for separation. You will have two cavities. You won't have core and cavity, but you'll have two cavities coming out, and you can use that to separate the two cavities, and then use SolidCAM for machining the entire part. I believe there are no more questions. Thank you, Goran. Thank you for the feedback. I believe there are no more questions. In event there are questions, you could always write to us. You have got the email address, and tomorrow you're going to get the email because you've attended the webinar. You'll get the email with the link of the recording so that you can watch this offline. Thank you very much, and have a nice week. Have a nice weekend.